Now we're going to look at what happens if we take the x in the sine or cosine and multiply it by some number b. And to start out, we're going to assume that b, the number we're multiplying x by, is a positive number. So for example, this would be something like the graph of y equals the sine of 2x. Okay, so now the multiple is inside the trig function, it's multiplying x. Just like when we took a sine or cosine and multiplied it by some number a on the outside that shrunk us or stretched us vertically, now multiplying x by some number is going to stretch or shrink us horizontally. So it's either going to stretch us out this way or shrink us this way. So you can think about it as kind of like stretching out or compressing a spring now. But this works in a kind of counterintuitive way, where if we multiply x by some big positive number, something that's bigger than 1, it's actually going to be a compression. And if we multiply it by a small positive number, something between 0 and 1, it's going to stretch us out. In general, it turns out that for y equals the sine of bx and y equals the cosine of bx, we can think about b as affecting the period. So the period is now going to become 2 pi divided by b. Okay, so now we can see how, if we believe this, multiplying x by a big number is going to make this period small, so it's going to make our graph transition very, very fast, and it'll kind of smush it. Whereas if b is a fraction, now 2 pi over b is going to be a really big number. We'll have a big period, and now it's going to travel very slowly along that period. Okay, so for example, if we looked at the graph of y equals the sine of 2x. Okay, so if we believe this, our period should be pi, should be 2 pi over 2. Okay, and we can check this by plotting some points. Okay, but now we need some more points than we usually use. So let's start at x equals 0. Now we'll do multiples of pi over 4. So pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So now we'll do all the multiples of pi over 4. And we'll do a column for 2x, and we'll do a column for our y. Okay, so notice what happens when we take x and multiply it by 2. So here I've just run x from 0 to 2 pi, but I've used the multiples of pi over 4. If we take those x's and multiply them by 2, now 2x becomes 0, pi over 2, pi, 3 pi over 2, 2 pi. So as we run x from 0 to pi, 2x is going through twice as fast because we're multiplying x by 2. So when the time it takes for x to go from 0 to pi, 2x goes from 0 to 2 pi. So there we've already completed one cycle because our sine values will cycle from sine of 0 to sine of 2 pi. So note here our sine values would be 0, 1, 0, negative 1, 0. Yes, that's one complete cycle of the sine graph. And we still have another pi units to go for x. So if x is 5 pi over 4, 2x will be 5 pi over 2. So now we're coterminal with pi over 2, so our sign will be 1. 3 pi over 2, multiply that by 2, we get 3 pi. That's coterminal with pi, so the sign is 0. 7 pi over 4, multiply that by 2, we get 7 pi over 2. That's coterminal with 3 pi over 2, so the sign is negative 1. 2 pi, if we multiply by 2, we get 4 pi, and the sign is 0. Okay, so now, and again, remember our x, and this is one place where some people can get tripped up. Once we finish up this chart, we don't have to worry at all about this second column. So we just use the second column as kind of like an intermediary. Okay, so that's going away. Our x is here, our y is here. Okay, so our x values will run from 0 to 2 pi in this case. Okay, so this is pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay, we're going to start at x equals 0, y equals 0. We go up to x equals pi over 4, y equals 1, and then back down, and down. So now I'm just plotting points and connecting the dots. And our graph will look like this. Okay, so we see that our amplitude is still 1, our domain is still all real numbers, our range is -1 to 1. We haven't messed with the y-coordinates at all, but now our period is indeed pi. Because here is one cycle of our graph. It runs from x equals 0 to x equals pi. And if we were doing y equals cosine of 2x, it would be the same sort of idea. That we'd have something that would look like a cosine graph, but it's going to be smushed because we're progressing through the angles twice as fast. Okay, so what happens if we multiply x by something that is negative? Okay, well, it turns out that we can use another property of the sine and cosine graphs to actually get rid of that minus sign and either delete it entirely or move it to the outside of the trig function. So for those of you who have taken or are currently taking Math 22, you have seen the idea of odd and even functions. If you have not taken those courses, no big deal. I'm going to touch very briefly on it and tell you what you need to know for this course. Okay, so first off, if we remember the graph of y equals sine x, okay, it looked like this. So the graph of the sine function has what we call symmetry about the origin. Okay, so what that means is that if we were to take this graph and turn it upside down or reflect it across the x-axis and then the y-axis, I like to think about turning it upside down, but either is the same, you get exactly the same graph. So if you think about this, you rotate it 180 degrees upside down, the graph doesn't change. That means that the sine graph is the graph of an odd function. So y equals sine x is odd. And an odd function has a property that f of minus x equals negative f of x. And odd functions, algebraically, they behave like odd powers of x, like x cubed, x to the fifth, and so on. That's why they're called odd functions. So for example, if you look at the function x cubed, if you were to instead take negative x cubed, well, that is clearly the same as the negative of x cubed, because either way, you're taking x cubed and multiplying it by -1. So for an odd function, if you have a negative inside the function, you can actually pull it out. So as far as we're concerned, this means that the sine of minus x is equal to negative the sine of x. So when we're dealing with a sine function and there's a negative inside of it multiplying the x, we can actually pull that minus sign out. So for example, if we wanted to graph y equals the sine of -3x, since the sine function is odd, we can pull that minus sign out and instead do negative the sine of 3x. And this is going to be sort of a combination of what we did in the last video and what we're doing here, where we're going to flip the graph upside down because we're multiplying the function by -1, and then we're also going to be manipulating the graph horizontally, and our period will be 2 pi over 3. So in this case, there's also going to be this additional flip upside down. similarly, if we looked at the graph of the cosine function, okay, so y equals cosine x, okay, we see that the cosine graph also has symmetry. It's symmetric about the y-axis. So two sides of the graph on either side of the y-axis are mirror images of each other. This means that the cosine function is even. Okay, an even function has the property that f of negative x is equal to f of x. Okay, graphically, even functions behave like even powers of x. So for example, if you had x squared and replace the x with minus x, well, negative x squared is the same as x squared, because the negative 1 squared is 1. So what this means for us is that when you are multiplying the x inside a cosine by a negative, you can get rid of the minus sign. So cosine of negative x is equal to cosine x. So for example, if we wanted to graph y equals the cosine of negative 3x, we can use the even power of the cosine and say, well, this is just cosine 3x. Okay, so we never have to worry about a negative multiple of x inside a sine or cosine, because we can always use these even and odd properties to either pull the minus sign out or just delete it entirely. Okay, so that's what allows us to generalize to b's that are less than 0.